Hello everyone, this is the lecture for section 4.7, exponential and logarithmic models. So all through section 4.1 through 4.6, so basically everything up to now from chapter 4, we've learned just how to play around with exponents and logarithms, right? Now we're going to put them to use, okay? I believe I said it in class, right? In real life, right? In actual nature, right? Um, if it's not linear, um, the next two things that it can be are polynomial and exponential, right? Um, and it it tends a little bit more to the exponential side. You'll see more exponential stuff in your physics, in your chemistry, in your math than anything else. Okay, and this is the section that we're going to cover specific models that show up on a regular basis, like a lot. Okay, um, the three that I'm going to be covering in this section is at least three models that we're going to be covering. They're exponential models, but we need the logarithm to sort of work them backwards. Is the exponential growth and decay. One of the other models is Newton's law of heating and cooling. And then the last one is going to be what's called the logistic model. Okay. And each one has its speciality, right? And they pop up fairly common, right? In not only math, but like places you didn't think you would expect it. Okay. So let's start out with uh, exponential growth and decay. Okay, that is this equation right here. A sub t is equal to a naught e to the kt. Okay, so let me fill in the stuff. A sub t, this tends to give us a future value, right? Given the time, right? Given the time t, right? Okay. A sub t tends to be, or sorry, a naught is what we call the initial amount, right? And t usually means time, okay? Whatever time that may be, right? You're not restricted to a year in this case. You can be restricted to hours. You can call this minutes. You can call it weeks if you wanted to, okay? K is the exponential growth or decay rate. Okay. Um, Whenever you see the word exponential growth or decay, right, or continuous rate of decay or growth, it's talking about this k right here in particular for this function. Okay. Some nice stuff about exponential growth and decay, right? If your k is bigger than 0, you know it's growing, right? Or increasing, right? If your k is less than 0, right, it is what we call decay, right, or decreasing. Okay? All right. So to show you guys how important this stuff is, right, this is something that happens fairly regularly in biology, right? Let's say you had a population of bacteria that doubles every 3 hours, right? If the culture starts with 10 cells of bacteria, right, come up with an exponential model, right, that models its growth. Okay, so automatically we know this, that our function is going to be some a sub t, right, a naught e to the k t. Okay, from the statement, we know we're starting with 10, so we can automatically say that it's going to be an a sub t equal 10 e to the k t. Okay, now we're going to use this right here, that this bacteria doubles every 3 hours, right? So at, right, t equals 3 hours, right, my a sub t has to equal 20. Okay, now why, right? the thing that we're missing here to fill in is that K, right? So that's what we're going to go find right now, okay? And we're going to use this little bit of tidbit of information right here to find it, okay? So then this is basically saying now, right, that my 20 has to be equal to my 10e to the kt, right? I need, oops, sorry, not t, 3, right? Because it's 3 hours, right? And actually, I'm going to put that 3 right here as well. 3 is equal to 20. Okay, so then 20 equal 10e to the 3k. I want the e to the 3k by itself, so divide by 10. Divide by 10. 2 is equal to e to the 3k. Here's where we're going to have to do our almighty boomstick, right? So a to the b is equal to c. That is equivalent in the logarithmic form to log base a of c is equal to b. This is the thing that we're going to use again. Okay? So in this case, we have the left-hand side. I'm going to change it to the right-hand side, right? So this is basically saying, right, 3 to the k is equal to log base e of 2. Okay? And then I need my k by itself, so divide by 3, right? So then I'm going to go up here. My k is going to be the ln of 2 divided by 3. And if you compute this out, you get about 0.231 and change, right? So my final model for the growth of this bacteria is going to be 10e to the 0.231 to the t. We are done. Bam. Okay? All right. So what we have here, right, is an exponential model, right? And notice what we're given. We're not given very much from the beginning other than 2 measurements, right? That we start out with 10, and at 3 hours, right, it should double, right? And just from those 2 pairs of information, we're able to get an equation for our growth. Cool? All right. Practice, practice, practice. I will have you guys do these in class. It just so happens, right? Hopefully you guys see this, right? We have this thing called a half-life. So in chemistry, in radioactive chemistry in particular, right? There are certain substances, right? They are radioactive, and what happens is that they decay to something else. Okay, so plutonium, for example, right? If I recall correctly, plutonium has a very long half-life, and it expels radiation, right? And what gets left behind at the very end is lead. Just lead. Just, the stuff that used to be in paints, used to be in gas, that stuff, right? So plutonium decays all the way down to lead if it lets off enough radiation, right? In order for us to measure how much our radioactive substance is decaying into something else, right? We have this thing called a half-life. The formula for the half-life is this right here. Okay. In particular, this is going to be very helpful in having us find our K value. Okay. So it's a quick way to find our K value. Okay. So let me show you guys what I'm talking about. We have the half-life of carbon, right, being 5,700 years, 5,730 years, right? I want to express the amount of carbon-14 remaining as a function of time. Okay, so what I'm going to do, right, is I'm going to use this newfangled equation that we have, right? So we know that a half-life is going to be 5,730, and it is going to be equal to negative the ln of 2 over k. Okay? And when we solve this out, right, I'm going to get k is equal to negative ln of 2 divided by 5730, which is going to be equal to, point, whoops, 1.2096 times 10 to the negative fourth. So that is equivalent to let me get this right, 1, 2, 3, 4, 1, yep, 0, 0, 0, 1, 2, 0, 9, 6. Let me get this right really quick. 1, 2, 3, 4. There you go. Negative. Okay, so my A of t is going to be equal to some A naught. This is still dependent on my initial amount, right? E to the negative 0.00012009t. Okay. Now, it just so happens that this element, carbon-14, is radioactive, right? And it is found inside our bones. This is actually the mathematical basis for radiocarbon dating. Okay, you can grab a bone. We know how much carbon-14 is supposed to be in a live bone, right? And then it slowly whittles away over time, right? To the point where if we know how much we have at any given point, right, we can actually measure how old the bone is. Okay, so for example, right, let's say we had a bone fragment that is found to have contained 20% of its original carbon-14, right? So we find a bone after so long, right? And it's only got 20% of what we know it had to have had, right? So how old is the bone? We're going to grab our equation, right? It's our A of t. We know that there's supposed to be 100% left, right? E to the negative 0.0001296t, right? And we need this to be equal to now 20% because that's what is left, right? Okay, so then now we are off to the races. So divided by, not divided by 20, divided by 100, divided by 100, okay? E to the negative 0.00012009t is equal to 1/5, if you reduce that, right? So then now, right, negative 0.00012009t is equal to ln base E, right, of 1/5. I can now divide by my horrible decimal number that's right there, right? Negative 0.00012009t. Divide that by the same thing, negative 0.00012009, not the t, sorry. Right? So then our t is going to be the ln of 1/5 divided by negative 0.00012009. And if you compute this out, you get about 13.312.14 years. There we go. Bam. So if we find a bone fragment, right, and we know how much of its original carbon-14 was supposed to be there, right, upon its death, right? And then we, uncover this bone, and it has only 20% of it left, right? Because of all the math that we just did, and because of the knowledge that we have about carbon-14, right? We know that that bone is a little over 13,000 years old. Cool stuff, huh? Woo! All right. Moving on. This one's pretty cool. This one's got a nice little history behind it. I'll probably tell you guys in class. Newton's law of heating and cooling. Okay. Uh, this one actually is one of the topics that you learn in when you get into thermodynamics for physics, and when you start looking at heat exchange or energy exchanges in chemistry. Okay. Um, and it's exactly what you think it is. It dictates, right? It at least finds a formula, right? It helps you find a formula for the heating of an object or the cooling of an object. Okay, the equation is this one right here. Okay, and all the bits and pieces are right here. Okay, the T is the time. Usually a time for this would be usually in minutes or in seconds or in hours. Okay, A. A is the difference between the initial temperature of the object and the surrounding. So this is where it gets a little funky. I'll explain it in the example that's below. Okay, and then K is a constant. It's considered the continuous rate of change of cooling of the object or of heating of the object, right? So you can imagine, right, that for heating, the K is going to be something, and for cooling, the K is going to be something. Okay? All right, so let's get into the example. Okay? Suppose I make a cheesecake, right? And I take it out the oven, and the cheesecake itself, okay, has an internal temperature of 165 degrees Fahrenheit. And I grab this cheesecake and I put it into the refrigerator that is set at 35 degrees Fahrenheit. Okay? After 10 minutes, right, I stick a thermometer in it, and the cheesecake turns out to be 150 degrees Fahrenheit. So it hasn't cooled much, but at least I have a measurement that at 10 minutes, it's at 150 degrees Fahrenheit, right? How long will it take the cake to cool to 70 degrees Fahrenheit? Right? Okay. I forgot one thing of our equation. The Ts is the temperature of the surrounding air. Okay, that is going to be important. Okay, so what I want everybody to look into first, right, is picture this in your mind, right? I grab a cheesecake that's been in the oven, 165 degrees, and I grab it and I stick it uh, into the fridge, which is 35 degrees. Okay, got it? Okay. So the reason why I have to I want you guys to read that over, right, and just picture it in your mind, is because that's going to be what we're going to be using for our A of T. So it's going to be A E to the KT plus my TS, right? Okay. In this scenario, my surrounding air temperature is going to be this 35 degrees. Okay? And so I'm going to write that first, 35 degrees Fahrenheit, right? And my A is going to be the difference between the initial temperature of my thing and the temperature of the surroundings. So keep this in mind, right? This is what gets a little funky. It started out at 165 degrees, and then I'm sticking it into a fridge that's 35 degrees, right? there is a difference in temperature there, right? So the difference in temperature is going to be the 165 minus 35. And that's going to be 130. Okay? This already gives us a fair amount, right? So this gives us this. A of t is going to be 130 e to the kt, right? Plus 35 degrees. Let me get that degrees out of there. Okay, so we're getting closer, right? We've figured out these two things. We figured out the A and the T sub S. Okay, now we're back to this thing. We need to find that value K. Okay, and in order to do that, we are going to use this portion that after 10 minutes, the cheesecake has cooled to 150 degrees. Got it? So then that means that when I do A, that's a little bit too separated away. If I want to do A of 10, that's going to be the same as the 130, right? E to the K times 10 plus 35, that has to be equal to 150 degrees. I get to solve this thing out. Okay, so at this point, we're off to the races, right? So I want to do minus 35, minus 35, 130 e to the 10k is equal to 115. I need this thing by itself, so divided by 130, divide by 130. E to the 10k is going to be 115 over 130. I'm going to leave that. I can reduce it. I can divide 115 and 130 by 5, right? But I'm just going to leave it. I'm just going to ride with it, okay? Our boomstick, right? So I'm going to write it up here, first of all. A to the B is equal to C. That is equivalent to log base A of C is equal to B. Whoops, B. Okay? So then that means I can grab this thing down at the bottom, turn it into my equivalent logarithmic form, right? So this is going to be 10k is equal to log base E of 115 over 130, or the ln of 115 over 130, right? I'm going to rewrite it really quick. 10 to k is equal to the ln of 115 divided by 130. Divide by 10, since I want my k by itself, right? K is equal to the ln, and I did it too big already, ln 115 divided by 130 divided by 10. And if you compute this out, negative 0.00425. And make it look nicer. So we have our equation now, right? So my A of t is going to be the 130 e to the negative 0.00425 t plus 35. Okay? Whew. This is the equation that models the temperature of my cheesecake. Okay, now the next question is asking the last bit right here. How long will it take until the cake cools down to 70 degrees, right? We have our equation, so guess what? We use that equation. I'm gonna scooch this over a little bit. So then we need our I'm going to go from here. I'm going to go like this, right? We need our 130 e to the negative 0.00 425 t plus 35. We need this equal to 70 degrees, right? Okay, we're solving for time. So minus 35, minus 35, 130 e to the negative 0.00425 t, 5t is equal to 35 divided by 130 e to the negative 0.00425t is equal to 35 over 130. I'm going to use that boomstick again, the thing in the orange, right? Negative 0.00425 t is equal to ln 35 divided by 130 divide by the stuff that we need, right? Our time is going to be ln 35 over 130 divided by my negative 0.00425. And if you plug this into a calculator, you get something around the lines of 106.7 minutes. We are done. Bam. Whew. Let me move this over a little bit so we can get the, come on. Okay. So all of this work, right, was to find two things, right? We needed to find this thing first. The equation that modeled the temperature of our cheesecake, right? And then we use that equation to find the time that it's going to take for it to get down to 70 degrees. Okay? Notice what we used basically everything from chapter 4 at this point, right? Okay. Woo. Moving on. I've got two of them here. I've got a cooling problem and I've got a heating problem, okay? I know the cooling problem is going to seem, the heating problem is going to seem a little more difficult, but it is not that bad. It's not too far different from the steps that I showed you guys from up above, okay? Okay, I'm going to go ahead and give you guys the time in class to try these out. These are going to be pretty difficult just altogether because of the amount of math, right? So a good solid half hour, okay? All right, moving on. The last one, logistic growth, okay? So logistic growth is this equation right here. Hopefully you guys see it. I know it's a little grainy. Nothing in the universe is truly exponential, okay? What we say is just the exponential portion of anything that you see, right, is usually the beginning of the logistic growth model, okay? Since nothing in the universe, at least from what we know, right, since nothing in the universe is infinite, right, anything that starts to grow exponentially should taper out, should sort of die off after a little while, okay? That's where this idea behind a logistic growth model comes from, okay? So there's a couple things that I need to cover for it. This C divided by 1 plus A, basically this little bit right here, this chunk right there. There we go, right? That is what we call the initial value, okay, whatever that amount might be, okay? The C is what we call the carrying capacity. This is something that the exponential equation or the exponential model doesn't come sort of pre-built with, okay? Since I said nothing in the universe is infinite, right? There's got to be a maximum somewhere, some way, right? That's what this C is taking care of, okay? And then last, this thing has a B. It's a constant growth rate, right? But we call it the logistic growth rate, okay? There's not much more I can explain behind the logistic growth rate other than that's what it's called, okay? If you need to know more, okay, that explanation, the explanation for B, is going to show up in your differential equations class. It's probably one of the last classes that you're going to need to take before you actually start your concentrated study, whatever that may be, engineering, physics, chemistry, the harder math, whatever that may be, okay? So I will defer the explanation for B till differential equations, whenever it is that you take that, okay? All right, so, excuse me, logistic growth. The prime example for logistic growth is the growth of a bacteria, right? Or the growth of a sickness through a population. Okay, so here's an example of how we can use the logistic growth model in such a such a scenario. Okay, suppose, right, we have influenza that spreads through LMC Brentwood. Okay, influenza, your practical, good old, normal, regular flu, right? Okay, at any given day, right, at LMC's Brentwood campus, there's maybe about 1,000 people, give or take, right? Okay, and suppose, right, at day 0, one person gets sick. Okay, so that means one person is going to show up to the Brentwood campus, and from that one person, everybody's going to get sick, right? Our biology department figures out that the logistic growth rate for influenza, for the flu, is going to be that. It's going to be B equal 0.6030. Got it? Okay. We are going to, first of all, construct the logistic growth model for the influenza outbreak at LMC Brentwood. Okay. How many people will have the flu in 10 days? When are the cases increasing the fastest, right? And how many people will have the flu as time goes to infinity? And why does this make sense? Okay. So some of these questions, we do need to break out our algebra for it, right? And some of these we can use the graph that's at the right, okay? But we're going to try to tie both of them together, okay? So first of all, let me do A. Construct the equation. So we know that it's going to look like this thing up here, right? It's going to look like, let me move up a little bit, there we go. One plus A E minus B X, right? It's got to look something like that. So I'm just writing it down for now, right? Okay. So our B we have already. So I'm going to do C divided by 1 plus A E negative 0.6030x. All right, we're making some progress, right? Okay. What I want to point out is, let me go back up here. C is what is called our carrying capacity, right? And what the carrying capacity is basically in the environment that's present, right? What's the most, right, that can possibly happen? right? What is the most that this scenario can possibly carry, right? And that means our C is going to be the 1,000. Okay, and the reason why is because in the environment that's been given, right, in the environment that we have in front of us, right, at any one time, there's only 1,000 people at LMC Brentwood campus, right? That is our scenario, right, can only carry 1,000 people. That is our limiting number, right? So filling in that, we get this, right? 1 plus A E negative 0.6030 X. Okay, so we have that A that's missing, right? We have the A that's missing. If we look up here, the A should be our initial value. Or sorry, the C divided by 1 plus A should be our initial value, right? And our initial value is given right here. We're saying that at day 0, right, there was 1 person sick. So then that means our 1,000, 1 plus A should be equal to 1. If you solve that out, right, 1,000 is equal to 1 plus A. A is going to be equal to 999. That gives us the final piece that we need. F of X is equal to 1,000 divided by 1 plus 999 E 0.6030x. We are done. This is the equation. This is the equation for this function right here. Okay? This equation models the progression of the influenza spread at LMC Brentwood campus. Got it? All right. We've got the equation. The rest should be cakewalk, right? So B. How many people will have the flu in 10 days? According to our graph, should be 294. It's exactly how you think we would compute it out, right? So we have F of 10, 1,000 divided by 1 plus 999 E 0.6030 times 10. And that gives us the 294. It's about 294. I'm going to write it that way. I'm going to zoom. It's a decimal value, but it's close enough. I think it's 293.95. Okay. All right. C. When are the cases increasing the fastest? So I'm going to zoom out a little bit so we can get more of the graph and more of our work. Ugh, come on. Uh-oh. Technical difficulties. There we go. Okay. So if you take a look at the graph, right? When will the cases be increasing the fastest? Hopefully you guys see it's like right around here. That is where it's the steepest, where the day-to-day, right, the cases are increasing the fastest. So I can go ahead and say that's going to be about what? Between 10 and 14 days, about? Between 10 to 14 days. Okay? All right. Last one. Letter D. How many people will have the flu as the time goes to infinity, and why does this make sense? So this is actually talking about the end behavior for the logistic curve. right? And what we're trying to say is this, right? That as our time goes to infinity, so if we go that way forever, right? What's happening to the number of cases, right? And hopefully you guys see it levels off at 1,000, right? It levels off at 1,000. Why does that make sense? Let me go back to draw. There we go. It levels off at 1,000 cases, right? So why does that make sense, though? If you take a look at the scenario that's been given to us, right? Uh, there's only 1,000 people that show up to LMC Brentwood campus, right? So you can't have more people get sick than show up, right? Does that make sense? Since there's only 1,000 people that can get sick, the worst, absolute worst, at the very end, right? If you let this, draw out till the end of time, right? The most that can get sick is 1,000 people because that's just the number of people that show up to LMC Brentwood campus, right? Right? So only, right, 1,000 people are at Brentwood, right? So that's the limiting factor, right? So that's got to be the limiting or the carrying capacity of this scenario. That's it. That is it. Okay. All right. Besides that, I think what comes up next is lecture questions, horribly spaced, but it's lecture questions nonetheless. If you have any questions on the stuff that we did, this is going to require a fair amount of time. Okay. There's a lot of parts where people can mess up in terms of the arithmetic or the algebra, right? So just keep a track of everything. Okay. If there's any questions, ask me during our quick check times or ask me during my office hours. Sound good? Besides that, happy studying.